Any questions? So if that English result is first section, then this Griffith is in the bookkeeping as the second part. And this naturally leads to the third part. I know this bookkeeping is always quite tedious. So, yes? Yeah, so as I keep complaining, we should have invented more than 26 letters. And yeah, so E is Young's modulus here and not, oh, I'm so sorry. Yeah. Okay, hold on. In my notes, I think I had something like, to honor Griffiths, I had something like EG. So, sorry, that we must do. So this is Young's modulus, right? And now I call the EG as this energy release rate, as the oh Lord, as the, oh Lord. This is the. Remember I said from going from A to B, you would have lost this much energy. So this is the total energy loss if you were to create a cut of size A. Is that clear now? Yeah, so basically it's otherwise, basically this volume would contain how much energy? Well, multiply the energy density, because energy density is the energy per unit volume. Thanks for, yeah, for
Given that the E and Griffith's law that you have out of sight, that is also.
So this E is Young's modulus. So I apologize. The only part that EG is involved is in this definition of energy release rate. And this E is Young's modulus. So E is E. So I think what I was casual was to omit the fact that I should have differentiated this. I did verbalize this. This is the energy loss, but to add more confusion to you, the energy per unit volume always have the same dimension as modulus as stress. And you will see all that coming. So in fact, this reminds me to make a comment before I forget. A rather critical comment. The critical comment is this. If you really need fracture mechanics, which means these two are happening, then you realized the game has changed. What game? The game previously, innocently, in fact, that is our polymer, by the way. Our polymer, let me give you the conclusion. Our polymer is not like window glasses. You don't need to blame flaws. In that limit, how you characterize your material? Well, one way is the nominal strength. What is the second variable? Well, Young's modulus, it gives you a sense of stiffness. What is the third variable? Well, maybe the strain energy density, which in the boring linear elastic limit is nothing but sigma. In other words, you only have two variables. One is the strength, the nominal strength. One is Young's modulus, because the third one is given by the first two. Let me repeat. In a much simpler case where fracture mechanics is disinvited, meaning you don't need fracture mechanics, these two variables are all you need to characterize. window glasses that apparently, I'm going to save some time, apparently does have flaws. Of what size? To reduce the window glasses from a 7 gigapascal to 200 megapascal, you just turns out to have flaws, and the flaws simply need to be of a size of microns range or so. If we ever get to my explanation of it, but this is just for your information. And whenever we have a flaws, we tend to use a star superscript to indicate it was not my intentional notch or crack. It was just what's inherently in the system. So we call it size, A star. When you have such a material, stress is not enough to describe the system, to characterize your material. And you know exactly why it's not enough. Because in addition to some kind of stress, a length scale pops out. A length scale pops out. Implying now your characterization must involve both a stress and a length scale. We need not go further than Griffith's expression for you to realize, aha, that's indeed the case. There is a stress, but in addition, there is a length scale, which is the size of the flow or of the cut. We'll come back to further description of this much later. So let me now comes to what we called the so-called stress intensity factor. K. In fact, I already showed you why we need such a quantity. You look no further than here. Sigma C is proportional to square root of A in the denominator, which is the same as saying there's a proportionality constant called Kc, which by identification is nothing but square root of 2 gamma E. So this is a constant. Usually people implying that somehow Kc is a material property. Okay? And in the case of Griffith's account, indeed it's a material property because it depends on Young's modulus and surface tension. Bingo. So this is a tremendous success of Griffiths trying to explain how window glasses was much weaker. It's weaker because during production, somehow, what is this level? This is a level you can not easily visually inspect and find them out. A micron is about twice of the wavelength length of light. It hardly will scatter light, and you may not see it. So it turns out, I'm going to be slightly sketchy here. It turns out in linear, linear elastic fracture mechanics, which is what Griffith and Inglis was doing. Linear meaning, let me just remind you what we mean by linear. For example, this is true, and everything is done in the limit of small deformation, meaning it breaks in a few percent, so epsilon is very small. Epsilon, as you know, is nothing but L over L0 minus 1. So in this linear fracture mechanics, actually, it's possible for you to show that this new quantity, K, I will repeat this quantities many, many times in the future. This K is nothing but Young's modulus times G. Oh, if you want the factor of 2, that's the factor of 2 because. So what I'm trying to say is, when K become Kc, that's when G become 2 gamma, and then of course I recover my formula of 2 gamma E, which is what I had here for you. So, let's use an English result to appreciate this quantity K. Remember the English result. English says its tip stress is twice sigma square root of A divided by square root of rho. Yeah? Just try to recall that's your English result. And therefore, and G is sigma squared E A. So I'm just trying to do a few things. Then in this notation, I'm going to ignore the pi. This is nothing but sigma square A, and therefore is nothing but K squared, meaning this K shows up in the English solution, actually. It's a very funny piece of mathematics. On the left-hand side is the stress. On the right-hand side, in this linear elastic limit, K, by definition, is square root of A times sigma. It turns out, sorry for the complication, it turns out if you are insisting on being accurate, you will find this K is precise. What I did precisely missed a pi in the square root. Let's not bother about any of this mathematical details. The key point is K is a loading parameter. In other words, I absorbed the nominal stress in the definition of K. So when you speak about K, you're already speaking about how you are loading, how you are stretching your material. And it shows up in this manner. Oh gosh, how much time you really have to agree with me. You need to spend a few hours to appreciate what K is, because K doesn't really tell you much. It is the K. Remember, K involves the cut size. And the cut size is nothing until you think about the cut size relative to the sharpness of that ellipsoid. I know, don't need to sweat over this. This is just I'm laying out everything in front of you only because I introduced the K as something quite important as a variable. It gives you the appreciation that the K can be larger either by having a larger cut size notch or a larger load. It will produce the same result because the result is what's happening at the tip. So it's a very funny thing. It's a very funny thing, but you also start to appreciate how K is capturing something. K contains a combination of stress and length scale. So K is not a stress anymore. It is this new quantity that's capable of accounting for fracture behavior involving length scale and stress, both. Let me go on a few more steps, then you will be, which I use K again. Then you will start to grow more familiar with it. And that is, before I do that, so if I follow this outline, that is, I'm going to show you a few more mathematical details. But before that, let me come to the punchline. Here is the most alarming part of the all. When I learned fracture mechanics, I struggled, I perplexed, and I start to lose sleep, and that's where it happens, okay? So the following is all you need to pay attention to, in fact. This is all wonderful for silicon glasses. That the material really just break when the energy release is about the surface fracture energy. Everything makes sense. And if that's the case, indeed my Kc is a material parameter because look at it. It's Young's modulus and surface tension. So of course it's a material quantity. But what about other brittle materials? Let me not even, well, historically, of course, the first thing you worry about is metal. And there were confusions as I conversed with our last week's speaker that they may worry about this metal being above or below the brittle ductile transition. And in fact, a lot of data was examined somewhat above brittle ductile transition. Then it's really complicated. So above means if you draw your material, your steel, it has a tendency of doing something like that, yield a little bit. It may not completely draw, but it has the feature of yield. In that limit, people carry out this, right? Today I introduced you a word called single edge notch. In other words, forget about doing it internally, just make a cut on the edge of size A. And you can start to get busy, measure what is GC, because GC is operationally defined simply by this. I'm going to omit the prefactors, okay? It's simply defined by this. I know I went through fast, but isn't that what we just said about Griffiths identified a point? I actually jumped quite a bit here. Your energy release rate is always just sigma Young's modulus and cut size. It's a variable because it depends on how much I'm loading. So let's make sure we differentiate what we're doing. Energy release rate is G. It changes as I load it more and more, as I stretch more and more. This critical, where do I have it? This critical energy release this critical energy release rate is when this G reaches some threshold, which Griffith teaches us should be what the surface tension prescribes. And the reason I review and try to write it down for you is throughout the history in the past 100 years, we agreed to call that toughness. Okay, so that's toughness. And this is toughness. So, oops. So let me say the most crucial part of all now. Remember, for your window glasses or silicon glasses to be precise, gamma C at fraction, it's the energy release rate you can define at the moment of fracture, is about the surface tension. For your metal, maybe because you are doing it above BDT, maybe for some other reasons, you find this GC is no longer gamma, 100 or even 1,000 times greater than gamma. By the way, I also learned remember, we went through brittle ductile transition problem. We know your brittle glassy polymer, such as your PMMA at room temperature. If you make a measurement, which was done in 1961 by Barry, who learned about fracture mechanics. Hold on, why are you playing with fracture mechanics for your polymers? Well, precisely, let me go to the first minute of this lecture, because we thought 50 megapascals is so weak, there must be flaws. Otherwise, why would go ahead and do this? So he went ahead, made so-called single edge notch. And lo and behold, he found Griffith's laws to be true. Meaning, he lovely found that, that this is true. You can back calculate, which is what I said, which is nothing operationally this. It's also true, just like in the case of steel, that this is much larger than gamma. The less confusing part is indeed this is done at room temperature for PMMA. So there's no ambiguity. It's below BDT. So it's truly in the brittle region. Nevertheless, this GC defined by Griffith, and later we credit this as Griffith and Irwin. This GC, the critical energy release rate, is found to be much larger than surface Reaction energy for polymers. Folks, I hope you are really you are not confused by my multiple statement here. PMMA was made a cut and measured this GC and found GC to be much larger than gamma. I suggested the reason you're doing it is you suspect that your PMMA has a lot of flaws, and the only way to explain or study PMMA is to suggest that your nominal strength of your PMMA will be prescribed by this formula, where you pretend you have flaws of size of A star. So let me repeat what I said. If your sample is not flawless, but flawed, you perceive, then the whole task is about understanding, gee, what is this nominal strength? The way I determine what is this nominal strength is I do another experiment. Instead of counting on this unknown distribution of flaws, why not I make a big cut here with known size? From that, I could operationally determine at the onset of fracture what happened, and turns out to be given by this according to what? According to the definition of energy release rate, and according to the definition that sigma C is the critical nominal stress at fracture, right? So at fracture. And so once I decide that, I know how I can prescribe. I know how I can prescribe my what do you call this? Notch-free sample now. So how do I have this formula? I'm just looking at the same formula. Oops, sorry. I'm just looking at the same formula and perceive that when I have a flaw, my fracture occurs as this nominal strength, right? So for treating that flaw to do something like my notch, so we call this notch, right? Single edge notch. And this notch will give you breaking at that critical. In other words, we are saying this is that. This is that, right? Just so trivial. If you don't get this, and then it's only because you are not interested, not because of anything else. Okay, clear? So this is the whole logic. A flawless sample, go ahead and just measure it, because in a flawless sample, your nominal strength is your true strength, is your theoretical strength. Otherwise, do fracture mechanics. So you already could become confused why I say your PMMA is actually this case, not this case. But then why you still have Griffith's law? Well, that's because you made a gigantic cut, a notch. So big, the fracture mechanical effect comes in, meaning a big cut does lower your strength. I know this is actually a lot of things are buried behind this. But let me emphasize, I said this is the most crucial. What do I mean by this? What caused me to lose sleep? What do I mean by this? I learned 4 years, 4 or 5 years, 4 years, 5 years, that for other materials, unlike window glasses, this is true. Man, if this is true, how can I even justify Griffith's behavior? I can release enough energy to pay for the surface. Why it doesn't break? I load more. I load more. That's what this condition means, right? In other words, you can happily claim G goes to GC goes to gamma and call that a critical condition, and it's a material constant. But here, obviously, gamma cannot help you, so what is this GC? Do you follow me? Let me repeat this. Why there still exists this magic GC at which fracture occurs, but this GC is much larger than gamma, then what this GC means? Do you get it? I cannot make it more plain in English than this, given my broken English. I say this because I want to strike you and make you realize you become helpless. Because I just said, oh, then what is GC? This operational definition, which allows you to measure GC, does not tell you why GC is a constant and why GC has this magnitude. It does not. 4 years later, I gave a name, I call this operational definition of GC. Or you can use a better word, experimental's GC. It's definitely not the theorist GC, if you like to use that word. Are you with me? Does that trouble you? That you got this GC, but you don't know what it is. The reason you don't know what it is because it's much larger than gamma now. Oh man, how simpler can I get it? When it is gamma, I'm happy like hell, right? I'm dumb, but it's not. For your dear polymers. So I want to say two things unrelated. For polymers, GC is much larger than gamma. And separately, polymers, I have not given you the proof, but I will in the future. Polymers is flaw tolerant or does not get the strength you get not because they are flaws. So these are completely two separate statements. So at this point, I want you to be as unhappy as me, meaning I'm frustrated. What is GC then? The thing is the GC exists. So now let me talk about, remember I said we are lucky and unlucky Griffiths went beyond English. So let me explain both. If Griffith is happy with English result, and did not make this effort to make this energy argument to understand what fractal mechanics is. Assuming nobody ever worked on fractal mechanics ever since Griffith, then we would never have discovered the concept of this critical energy release rate, yeah? We would not have. He used the window glass as an example, guided him to identify this quantity called critical energy release rate, because that's the amount you pay for gamma, for the energy. But then disappointment comes as soon as the people look at other materials, says, this is garbage because gamma doesn't come in, because the GC is much greater. Miraculously, GC still survives in the sense of Griffith's law. So don't be confused. You have Griffith's law holding independent of the fact that this GC is much larger than gamma. And we will explain all of it in the given time. You know, we will, and soon. Okay. Soon. I really mean soon, because as a homework, if you do it, I tell you the answer is already in English solution. But we will not do it now. Because the homework, I don't want to give you a solution. So if you want to, today is which day? So if you want to think over it, you can. But I was losing sleep about Jesus Christ. The law is still there. Griffith's law is still there. Where is it? And KC is still there, except as in any textbook, the textbook quietly replaced the gamma by GC. Quietly. Yes? No. Okay. Yeah, always so. So I meant to say that it's a bonus. You know, it's a homework, not a homework that I'm going to formally assign. I'm saying you could go ahead and try to answer the question or the frustration. If GC is not gamma, what is GC? That answer is in English solution already. So please, for any of you interested, you can work out that homework. Call that a homework. Okay. Let me further emphasize and give you a partial answer already about this trouble of GC much larger than gamma. It goes back to what is the surface tension? Well, it's whatever energy required to break bond at the monolayer level. Okay? So recognize that. Does that give you a clue, by the way? that is the problem you are dealing with, not something that's happening at the monomer level. The real trouble, I think, I'm happy to be contradicted. The real trouble of this fact is that the textbooks start to write it that way, okay? So don't blame me for saying it. The people start to say, if you only need gamma, release gamma amount of energy for fracture to occur, why you need something thousands of times of gamma? You must have something wasted, dissipated, not used. Confusingly, very confusingly, when they try to work with metals such as steel, especially if you are above BDD, then of course there is plenty evidence of plastic deformation. Such that you would, by definition, envision there will be energy dissipation. I probably need ChatGPT or probably need the word expert to tell me. Energy dissipation, as far as I know, really there is only one form, that is viscous energy dissipation. Viscous, of course, by the time you have learned about, by this far in our courses, plastic deformation, of course, is one form of viscous. The nature of plastic deformation is viscous, dissipative, irrecoverable. So I'm inviting everyone to check out the textbooks. Can I ask a question? Where is the need to mention that energy dissipation must have been taking place? Two. One is the metal was examined sort of above BDT, so I do see a sense of a lot of plastic deformation taking place, which of course will lead to energy dissipation, meaning I see there. Secondly, I believe a good pressure coming from the fact this would be the way to explain why GC is much larger than gamma. There must be something that I don't have to pay, but I nevertheless consumed. I think I don't mind, people telling me otherwise. So that's how at least I could, sometimes you have nothing else but to put words in their mouths, right? So we're talking about textbooks. I checked 2 textbooks, both of them, Anderson's book and Sang and Jin's book. They both mention prominently. But keep in mind, the traditional fracture mechanics is all about dealing with metals. Polymer comes later in the 50s and 60s once they saw their polymers are brittle, and once they learned that you guys have been playing with that game of brittle fracture mechanics problem, let me borrow it, right? So that's how you had the Barry's first measurement. To close, I think there's no better place than before you forget, because I hammered on this point. to close I said how lucky we, too late for you to pray to God, but how lucky we were that Griffiths thought about doing it this way and identified a concept called critical energy release rate, which is GC, and it happens to apply to all materials that's brittle, despite the fact they are much larger than gamma. So that's the lucky part. The comment I want to make about unlucky is this very same approach also have the potential to mislead you to think that GC contains a lot of energy dissipation. Fair? It's plain English. I cannot do better. In fact, mathematically, we write GC as gamma plus the rest. The rest is largely plastic. Presumably, that our view is plastic work, therefore dissipated. How convenient. With this framework, the convenience is maybe this offers me an easy way to explain about the rate effect of elastomeric fracture. A short sentence about that is when we stretch faster, we find the GC faster with the crack. The GC is higher. GC is higher. See, we can do a peeling experiment. Peel the thing on the substrate, you peel. The faster you peel, the more force you have. And it turns out that more force divided by the width of that sample, or not width. Yeah, I know in the peeling it's a little bit more difficult. So it's better for me to tell you about so-called tearing. Oh Lord, where is it? I'm such a bad drawer of that. Basically, I'm not talking about this. Okay? So there's a way, I'm such a bad. So this requires certain force. That force divided by thickness of the sample has the dimension of GC. And therefore, I'm explaining that if you peel faster, you find the GC is higher, meaning the force is higher. And how convenient that this higher rate must involve higher energy dissipation, according to Newton's law, right? If you have a higher stretching, you should have higher stress, higher rate of stretching. So I'm being very informal and crude here because I run out of time. But I take some questions you have. Yes? Let me repeat, okay. First of all, you understand by now, it's such a powerful thing to think that GC contains a lot of energy dissipation, because that's how we can easily explain that it's much larger than gamma. I'm saying that perspective misled you or incorrectly convinced you that I can use the same concept of energy release, energy dissipation to explain the fact your elastomer, when I peel faster, I need more force. In other words, my GC increases as I do it faster. To explain why it is rate dependent and increase, how convenient is it to say that your energy dissipation, of course, grows with the rate? So you never need to look back. I have our problem solved. It's all energy dissipation. And that's a trap. So that we probably will not even be, likely we will touch on that next lecture, but maybe even later. But we'll definitely cover that because that's the, we talked a lot already about elastomeric rupture. Okay.